Hello, everybody. This is chapter 7 of our textbook on matrices and data frames. We're working with the part 1 slides from chapter 7, focusing on matrices. First of all, let me pull back and give you the big picture of the computer science minor at Georgetown College. It's essentially a data science program rather than general computer science. But we do include a year of basic programming. You're in Computer Science 1, CSC 115. We'll be continuing in CSC 215 with the rest of our textbook plus a few extra topics. And this gives you the basic programming coding skills that you need in order to handle data in the modern world. We have a year-long sequence in data science, CSC 303, Fundamentals of Data Computing, that's offered every fall. And then that's followed on by CSC 405, nominally about databases, but many other aspects of data science as well. That's offered alternate springs. So if you're interested in this minor, I would strongly suggest CSC 303 this coming fall. We also have a course that currently focuses more on other aspects of web programming outside of data science. It's a course where you learn JavaScript and learn how to write web apps in that language. That's offered alternate falls and will be offered on a course by arrangement basis this coming fall. You could also take that course with your CSC 115 knowledge, although I think that CSC 303 is really the next place you should go. Data analysis uses more and more the internet, both for collection of data and for reporting out on the results of your work. So you're going to see more and more integration of web tools, web programming, as you proceed through the courses in this minor. The kind of basic tools that you're going to learn is programming languages, and the one that you're learning right now is R, a language that was designed by statisticians for statisticians and has since become one of the major languages for people who work with data science. That you begin in CSC 115 with your R, and you'll use it in almost every other course in the minor. Many interesting things you can do with R beyond the programming that we're learning right now. You can actually make your own blog on the web and have it hosted for free at a number of hosting sites. That's typically done in CSC 405. You can write online web apps of the sort that I've been showing in class from time to time, and that you see all the time right now to do things like track the confirmed cases of coronavirus around the world. That's done with an R package called Shiny, and you learn some Shiny currently in CSC 215 and in 405. Programmers, when they work together on large projects, use version control systems, and you'll be learning about those in two places, in the web programming course, CSC 324, and in the second semester of data science. JavaScript is the other main language that you learn in the minor, and that is taught in CSC 324. There is structured query language, not a full programming language, what they might call a domain-specific language, that's all about making queries to large databases and managing those databases. And you get an introduction to SQL in CSC 405. So here we are at the beginning of this minor and still studying R. So as you know, any programming language contains a number of data structures, ways for human users to organize and present and store data for all sorts of applications. Because R was designed for data science, it does tend to support data structures that make data analysis easier. And in this chapter, our primary goal is to learn about the data frame structure for holding information. These are two-dimensional objects, or at least they can be visualized by us humans as two-dimensional objects. So in order to get us thinking two-dimensionally about data, we're going to learn about another more elementary data structure in R, matrices. So here's Morpheus in the Matrix movie. Do you want to know what it is? Well, in our course, a matrix is not some sort of large-scale device for deluding you into thinking that you live another kind of life. It's instead just a regular atomic vector, like all the other atomic vectors we've been dealing with endlessly in this course. It's just that it has two additional attributes that other atomic vectors don't have. It has a specified number of rows and a specified number of columns. Here's an example of a matrix down at the bottom. It has rows. Here's the first row. Here's the second row. There are 6 rows. And it has columns. First column, second column, third column, fourth column. So it's a 6x4 matrix, 6 rows, 4 columns. How did we make it? Well, we took the whole numbers from 1 to 24, bound the name numbers to that, and then we used a new R function called matrix. Matrix takes a vector of items and adds those two attributes, the number of rows, the number of columns, to make a matrix. The name numbers mat has been bound to that matrix. And here is numbers mat. It's important to note that the top things here are not part of the matrix. They are kind of clumsy names for the columns, and the things on the side are not part of the matrix. They're clumsy names for the rows. Now, because numbers has 24 items in it, you really don't need to specify the number of rows and the number of columns when you turn it into a matrix. You really only have to say how many rows you want or how many columns you want, and R will figure out another number for you. So if you say the number of rows is going to be 6, it'll take the 24 numbers in numbers, divide by 6, and figure out that it needs to have 4 columns. So this command here would give you the very same matrix. Now you'll notice that when we made numbers mat, the numbers from 1 to 24 got filled in down the columns. 1, 2, 3, 4, 5, 6 is the first column, and then continuing with 7, 8, 9, 10, 11, 12 on the second column, and so on. If you want the fill in to go a different way, like across the rows, all you need to do is specify that the parameter by row shall be set to true in your call to the function matrix. By default, it's false. You can specify it to be true. Numbers mat was made out of numbers, but you could make a matrix out of any of the types of atomic vector that R allows. Here, for example, creatures. That's a character vector of length 6. So we can make a matrix out of creatures. Here I am specifying the number of columns shall be 2. Therefore, we get a 3-row, 2-column matrix that is filled down by columns by default. If you have a matrix, like numbers mat, you can remove the row and column attributes, turning it back into a regular vector. All you have to do is use the as.vector function. And as.vector will take anything that it's given and try to make it into a vector if it can. Now, you can give better names to the row and columns of a matrix. So for example, numbers mat. You can give it as an argument to a function called row names. And the assignment operator here is allowing you to say that the row names are going to be the first 6 lowercase letters. And this next assignment command is telling us that the columns for numbers mat shall be named as the first 4 uppercase letters. And so now when we evaluate the expression numbers mat, we get what you see in the console. Those are somewhat nicer looking names. Of course, you could specify any vectors that you want to be the names for the rows and the columns. It doesn't have to be lower and uppercase letters. When we talked about vectors, we figured out how to take subsets of vectors. For matrices, we also need to learn the same thing. It's typically called matrix indexing. We will still use the square bracket to subset matrices just like we subsetted regular vectors. But the format's going to look a little different because matrices are two-dimensional. So if I wanted to get the element of numbers mat that is in the second row and the third column, then I would take numbers mat and subset with the square brackets, but I would put a comma between the 2 and the 3. What comes before the comma talks about the rows that you want. What comes after the comma talks about the columns that you want. The number 14 turned out to be at row 2, column 3, and numbers mat. Let's check that. Row 2, column 3, sure enough, it was 14. You can actually get more than one row at a time and more than one column at a time because the vectors that you put before and after the comma can have any length that you like. They don't have to be length 1 vectors. And so that can give you entire submatrices all at once. Let's get an example of that. Suppose that you wanted to get the second or the fourth rows along with the first, second, or third columns of the matrix. Then you take numbers mat, and before the comma inside the square brackets, just ask for 2 and 4 put together, rows 2 and 4. After the comma, ask for 1, 2, and 3 put together, 1:3. And sure enough, we get a submatrix with the B and D rows, the second and fourth rows, and the A, B, C columns, the first, second, and third columns. Now suppose you just wanted the second and the fourth row, and you were happy to have all the columns. Then you don't have to specify any columns after the comma. You can just leave it empty, and you'll get the entire column, as we see here. Or suppose you just wanted the first 3 columns and you're content to have all of the rows. Then just put nothing before the comma and then the 1, 2, and 3 after the comma to specify those particular columns. Now, there's one little twist you need to keep in mind. Suppose that you decided that you just wanted the first row of numbers mat and you're content to have all the columns, so you leave it blank. The output actually is no longer a matrix. It's a named vector with 4 elements. The names are the A, B, C, D, and they came from the matrix. The result is not a matrix, it's just a vector of length 4, 1, 7, 13, 19. R figured that when you asked for the first row, that you really only wanted a vector as a result, that you no longer wanted to look at it as a matrix. So it dropped the structure of the object down from the more complex matrix to a simpler regular atomic vector. Usually that's what you want. But if you really did want a matrix out of that, then go ahead and add on with another comma an extra argument where you set a drop parameter from its default value of true to false. Drop says I'm going to drop down, if I can, from a matrix to a vector type of object. Setting that to be false gives you results that actually are a matrix, and you can tell because there is now a row name. The A, the first row name, is still hanging on there. This result is an actual matrix, 1 row, 4 columns. Be careful not to ask for rows or columns your matrix does not have. Like if I ask for rows 2 and 3 and column 5 to make my submatrix, there's going to be an error because there's only 4 columns in numbers mat. So subscript out of bounds errors, typically you're asking for rows or columns that your object doesn't have. You don't just have to ask for the number places of rows and columns. You could use the names of the rows and the columns. So I'm looking for here the rows named A and C, and the columns that are named with the second and third letters of the alphabet, the capital B and the capital C, so I get this submatrix. You can also do logical subsetting just like you would do it with ordinary vectors. You're just using that comma inside of the square brackets to talk separately about rows and columns that you'd like to see. So for example, suppose we just made a vector of numbers 1, 2, 3, 4, 5, 6. Call it row numbers. And let's make another vector, a logical vector, produced by row numbers mod 2 equal to 0. So we're calling that row is even. And that's going to be true when the number is even, false when it's not. 1 is not even, 2 is even, 3 is not even, and so on. Now, let's do some selection on numbers mat, where before the comma, we say row is even. After the comma, there's nothing, so we're willing to have all the columns. The result is that you only get the rows where row is even was true. And so you get the second row B, the fourth row D, and the sixth row F. You can use subsetting to assign to a vector. Therefore, you can use subsetting to assign to a matrix because a matrix is just a special type of vector. If I want the second row, third element of numbers mat to be 0, I just say it this way. Numbers mat at the 2/3 place shall be 0. And sure enough, it now is. You can use R's recycling abilities to assign to more than one place in a matrix. Here I'm talking about the entire second row. Saying that it ought to be 0 makes R recycle that length 1, 0 vector into a length 4 vector so that it can make the entire second row zeros. If you want to assign different values to different places, you could do that as well. This assignment command is saying that the entire second row shall be 100, 200, 300, 400. And so it now is. You can do arithmetic with vectors, so you can do arithmetic with matrices. To make some examples, let's put together a couple of simple matrices. Mat1 here is the result of a call to matrix on the number 1 repeated 4 times, and it's going to be a 2-row, 2-column matrix. So here is Mat1. Mat2 is the same, except I'm making it out of the number 2 repeated 4 times. So here's Mat2. If I were to add Mat1 plus Mat2, then what R is going to do is work element-wise. It's going to say, I got my 1 here, I need to add it to the 2 here. I got my 1 here, I got to add it to the 2 in the corresponding place, the other matrix. This 1 has to get added to this 2. This 1 has to get added to this 2. The result is 3's in all the places. You can element-wise subtract and divide, and other types of arithmetic as well with matrices. Recycling applies in arithmetic for matrices just like it does for vectors. Say you take the numbers 1, 2, 3, 4 and make a 2 by 2 matrix out of them called mat. Here it is. Suppose we decide to multiply every element of mat by 2. We can write that as 2 times mat, because that 2, a vector of length 1, is going to get recycled into a vector of length 4, 2, 2, 2, 2. That'll be turned into a matrix of all 2's, and it gets multiplied element-wise by the 1, 2, 3, 4 matrix, resulting in the 2, 4, 6, 8 matrix that you see here. So we could have done it kind of longhand by saying we were going to multiply mat by that matrix of 2, 2, 2, 2's. But the recycling makes it a lot easier. Now, for those of you who are maybe math majors or minors or pre-engineers and maybe they've had a linear algebra course, you need to keep in mind that the multiplication, the asterisk, the star in R is not doing the matrix multiplication that you learned in linear algebra. If you want to learn how R does that kind of matrix multiplication, you can study the textbook in Chapter 7. We have a little section on it for you to read. Boolean operations apply to matrices because they apply to any vectors. The result is going to be a matrix of logical values instead of a regular vector of logical values. Let's take numbers mat, get back to its original state. So that's the numbers 1 through 24, 6 rows, 4 columns. And suppose we wanted to find out which of those elements are odd. You can just take that whole matrix, mod 2, and ask, is it equal to 1? And every place where there was an odd number, you now have a true. Wherever there was an even number, you now have a false. So the result is a logical matrix. Very nice. You can select elements from a matrix using such a Boolean operator. So suppose you want to look at the subset of numbers mat where numbers mat was an odd number. You get all of the odd numbers back, but you have to get it back as a regular vector, no longer a matrix, because those odd numbers don't necessarily appear in places where you could make a submatrix out of them. That's it on matrices. We'll be back for part 2 of the slides soon.